There's a hidden paradox at the heart of any system designed to make a choice. We assume more information leads to a better decision, but beyond a certain point, the opposite becomes true. This explainer will break down the mechanics of why that happens.
Our rational expectation is straightforward. As we get more data, our choices should get better. But what we see in reality is that systems hit an overload point. After that, decision quality doesn't just level off, it degrades, often sharply. What's crucial to understand is that this isn't about a person making a mistake. It's a structural property of the system itself.
Our analysis will move through 6 parts. We'll start with the paradox, then model the decision-making system, identify its core conflict, look at what happens under stress, see how breakdown emerges, and finally, define a general principle of overload.
So let's start with the information paradox. It's important to be clear. This isn't a story about human error or bad judgment. At its core, it's about a fundamental mismatch, a conflict between our rational assumptions and the very real physical limits of a system.
To really understand this, we need to step back and look at the act of choosing from a systems perspective. Think about it. Every single choice, it doesn't matter if it's made by a person, a team, or an algorithm, is simply the final output of a process. It's a system designed to do one thing: turn information into a selection. So, what does this system look like? Well, we can model it using just 3 core components.
First, you have the system's input. This is simply all the raw information that feeds into the process, all the variables, the signals, the data points, everything that's considered relevant to the choice.
Next, we have the processor. This is the mechanism that actually analyzes all that input. But it has one defining, absolutely critical constraint. Its capacity for handling information is finite. It has a limit.
And finally, there's the output. This is simply the result of the whole process. It's the decision itself, the course of action that the system ultimately produces.
Okay, with those 3 components in mind, we can now see the system's central conflict. It's a fundamental tension between the sheer volume of information coming in and the fixed, limited capacity available to process it.
And this chart really makes that structural imbalance clear. You can see how the volume of information could just dwarf the system's fixed processing capacity. It's this exact mismatch that creates the conditions for failure. Now, we can define this condition with real mechanical precision. Information overload isn't just a feeling of being overwhelmed. From a systems perspective, it's a very specific state that occurs when the input rate exceeds the processing capacity. It's a completely predictable outcome of that imbalance we just looked at.
So what happens when a system actually enters this state of overload? Well, it doesn't just speed up or work harder. Instead, it begins to exhibit very predictable modes of failure.
When the processor is overwhelmed, it stops functioning as it was designed to. Rather than producing better outputs, it starts generating errors and breakdowns. Let's examine 2 of the primary failure modes.
The first failure mode is analysis paralysis. Now, from a pure systems view, this is what happens when the processor is so flooded with input that it simply can't produce an output anymore. The volume of data creates a kind of processing gridlock, and the system just halts. And the result we can observe from this state is exactly that. The decision-making process grinds to a halt. No choice is made. The system is, for all intents and purposes, frozen.
All right, the second failure mode is what we can call filter failure. As that processor gets more and more saturated, its ability to do a crucial job, to distinguish the important information, the signal, from all the irrelevant data, the noise, starts to break down.
The consequence of this is that even if the system manages to produce a decision, the quality of that decision is severely compromised. The output is now unreliable. It's far less likely to be the optimal choice because it's based on a foundation of noisy, poorly filtered information.
Now, what's really important to grasp here is that these failures don't just happen out of the blue. They are the emergent result of a sequence, a kind of cascade, that builds directly from the system's own underlying dynamics.
And this process unfolds in a predictable sequence. First, the input rate of information goes up. Second, the system's fixed processing capacity is breached. Third, as a direct result of that overload, the signal gets lost in the noise. And finally, the quality of the system's output either degrades or it stops altogether.
All of this allows us to step back and formulate a much more general principle, one that applies far beyond just one type of decision. We can call it the overload principle. And the principle is this: Any system that has a processing bottleneck, it doesn't matter if it's biological, computational, or organizational, is structurally vulnerable to this exact same pattern of failure.
What this really means is that overload isn't a flaw in the processor itself. It's a structural property. It emerges from the relationship between the input volume and the processing capacity. You could have a perfectly functioning processor, but if you place it in an overloaded system, it will fail.
And so, this brings us to our final conclusion. When we see a bad decision emerge from a situation with an abundance of information, we shouldn't see it as a mistake. We should see it as the system working exactly as designed. It's producing the logical, predictable, and expected response to being in a state of overload. The failure then isn't an anomaly. It is, from the system's perspective, the correct output.